Okay.
Uh, Hi, good afternoon, everyone. Welcome to the Formula Bharat Driverless Vehicle Workshop 2023. The topic for today's session is real-time simulation and its application in e-mobility using Typhoon HIL, hosted by Typhoon HIL. The topic will be presented by Ms. Ira Bajpai, application engineer at Quarbz Infosystems, which is the Indian franchise of Typhoon HIL. All participants are requested to note the following simple instructions. We encourage you to turn on your video during the session. Please mute your microphone throughout the session unless you are asked otherwise and during the doubt solving sessions. So without further ado, let's begin the session. Over to you now.
Thank you, sir. I'm just about to share my screen.
Yes.
So kindly confirm if my screen is visible. Is my
Yes.
screen visible? Okay, okay.
Yeah.
Thank you. So as you can see in the screen here, we are having an image of an EV diagram. So basically our today's topic is drawing an electrical vehicle, how to do the entire modeling, what are the mathematical calculations behind an electric vehicle design. And we have basically designed the entire model and we have broken it into 5 parts. So as you can see in this figure, we are having 5 different components. Basically, all are interlinked with each other and they are comprising an electric vehicle, a complete design of an electric vehicle. So as we know that electric vehicles run on batteries, so we have one component that is a lithium ion battery, as you can see on the left side in the screen on the PPT slide. Then next we are having this electric drive component. In drive, basically, as you can understand that we are having the motor component, which is developing the speed and torque signals basically. So it is getting energized, or the firing is coming from the battery and the power is given to the motor. And similarly, we are obtaining some sort of torque and speed signals. Next, we are having the mechanical transmission unit. Basically, in this unit, we are having the gear system. So as we know that in our vehicles, we are having different kind of gear systems. For that, we are having this particular component or subsystem that we are naming as mechanical transmission unit. So we will basically utilize some of the ratios like gear ratio, transmission ratio, and using that we will just simply convert the values of torque or speed signal into after product we'll get the some sort of force signal or the wheel velocity, which will then further be given to the next subsystem block, that is the vehicle dynamic. So basically in vehicle dynamic, as the name suggests, that all the vehicle parameters which are getting changed, for example, the wheel velocity will be changing, the acceleration force will be changing. So all these will be coming in a part of vehicle dynamics. And last but not the least, the main part is the vehicle control and EMS. Basically, EMS stands for Energy Management System. So all the control which is happening for our entire EV, that is being done by this block, that is a vehicle control block. And using this block, it is basically interconnected with all the components. There are some signals which are going as an input to this block, and there will be like 2 or 3 signals which are coming out of this block, and it is being given as a feedback to other components which are there in either electric drive or mechanical transmission, and the proper control of this entire vehicle is happening. So since this workshop is basically on the aim of Formula Bharat is basically for the UAV kind of vehicles, that is the unmanned vehicle. And this particular vehicle that we are going to design, it is the example of a normal electric vehicle that is running on the roads. But for this particular example, we are not going to use any like component which are basically weight wise heavy. What I mean by weight wise heavy is that if I'm having a Typhoon HIL simulator and I have some processing core inside it, so if I'm using a heavy component, for example, a 3-phase inverter or an induction motor, it is going to occupy some space in my processor. And that space is basically determining the speed of the simulation. So if my model is very heavy or very complicated, it is going to probably take some time to run. But today we are going to design the model which is completely going to run on signal processing components. So basically we are just transferring the signals from here and there, and we are using some reference drive input or the drive cycle. Basically a drive cycle is used to run the entire vehicle. Basically the drive train, the transmission, everything is happening through the drive cycle. So what kind of drive cycle we are going to use, and what is the mathematics involved behind this model? So we'll just discuss that more briefly. Just to summarize this slide once again, we are going to build 5 blocks in our model today. The 5 blocks are, first of all, lithium-ion battery, then electric drive, mechanical transmission, vehicle dynamic, and vehicle control. Now talking more about what are the type of forces that are involved in electric vehicle. So basically there are 4 types of resistive forces which are there in any sort of EV that you see on the road today. So we are having, very first of all, the rolling resistance. So what does the rolling resistance mean? So the force that the vehicle must overcome due to the rolling motion between the wheels and the surface of the motion of vehicle. So basically this is the force which is getting applied on the wheels with respect to the road or the surface on which it is moving. So this is, very first of all, the rolling resistance which is applied in an any sort of electric vehicle, not necessarily electric vehicle. Basically this is a force which is applied in any moving vehicle. Then second, we are having the grade resistance. So as the definition says, when a vehicle goes up or down a slope, its weight produces a component which is always directed to the downward direction. So basically this grade resistance is dependent upon what kind of slope we are having. So if our vehicle is going up or down the slope, and our vehicle is either, accelerating when going up or deaccelerating when it is coming down, so this kind of a grade resistive force is applied on the vehicle. Now, third one is the aerodynamic force. So basically aerodynamic force is vehicle traveling at particular speed in air encounters a force resisting its motion. So as I think the picture is quite clear, that when our vehicle is moving, the wind is surpassing the vehicle, and there is some encounter with the air, and that air is trying to resist the motion of the vehicle in its direction. And this kind of a resistive force is termed as aerodynamic force. The last one is the acceleration force, basically the force that the vehicle has to overcome due to acceleration of the vehicle. So M into A, this is a very basic force which we have always studied. And all the combined 4 forces, that is the 4 resistive forces, the rolling resistance, grade resistance, aerodynamic force, and acceleration force, together combine and form a resistive force. Now, resistive force, basically by the name resistance only we can understand, it is trying to stop the motion, or it is trying to like behave as an obstacle in order to stop the motion of the vehicle. So what we want is our vehicle to remain in the moving state, or whenever we want to turn the speed on or off, according to our application, we should be able to do it. So in order to drive the vehicle, we need to overcome this resistive force. So now, as you can see in the bottommost point of this particular slide, the net force. How is the net force which is driving the vehicle defined? So net force is equal to the traction force minus the resistive force. So the traction force is basically the tractive force or the torque which is being applied by the DC motor in order to run the vehicle. And that, when it is subtracted with all the combined resistive forces, that produces the net force. So net force is actually responsible for moving our vehicle. I hope you all got a good idea about this. Now, moving on to the next, motion conditions. So there can be multiple situations when we are talking about the net force. There can be 3 major cases which can happen. In this slide, as you can see, if we talk about case number 1, when our net force is equal to 0, what does that mean? So if our net force is 0, that means tractive force as well as resistive force, both are equal. And that time, the vehicle will not be moving, it will be in the stationary condition. Now, if we talk about case 2, when the net force is greater than 0. So when the net force is greater than 0, obviously our tractive force is higher and resistive force is lower. So when the tractive force is higher, our vehicle is in the acceleration condition and it is moving. Now, when we talk about case 3, when the net force is less than 0. That means our attractive force is less in value when we compare it with the resistive force. So in this case, the vehicle will be in the deacceleration condition. So these are three conditions which are possible for any vehicle. Either it will be stationary, in that case the net force will be 0. Either it will be in acceleration stage where the net force is greater than 0, or the deacceleration stage when the net force is less than 0. So this is what is the mathematical fundamentals which are involved behind the motion of the electric vehicle. And using these kind of formulas and these equations only, we are going to do the designing or the modeling of the EV in the model which we are going to prepare today. So this is one of the slide which I will also discuss later on once we are like we have made the entire model. So this is the drive cycle, as I was mentioning, that we are going to use this drive cycle in the model today. So what is the purpose behind using this drive cycle? Basically, as you know that for unmanned vehicle, there is no control which is happening from manually from the human side. So we have tried to replicate some sort of that unmanned thing in our this particular EV model. So by using this drive cycle, basically this is a graph between speed and time, and we have given various speed values, like it is in form of Excel, or you can understand X and Y components, so that we can make this particular drive cycle graph. And using those X and Y points, we have plotted this graph, and this is how we are asking our electric vehicle to move. So whatever model we are going to design today, it is going to follow this drive cycle. So we are not going to manually control anything. We are not going to provide any speed from our side in between the running of the model. This is the reference which our EV is going to have for today's model, and this is what it is going to follow. So somehow it will be automated. We are not going to do anything once the simulation starts running. So maybe you will get 1% of the idea how this unmanned vehicles have been formed, because the entire controller design is being given as a reference, and using that only the vehicle is moving. So now coming on to the part where we have to start the modeling. Yesterday, you all got a good idea about how our software looks like and what are the components in it. So now just we are going to jump in and we are going to start with today's model. So first of all, I'm going to select a new model. Either you can click on this yellow button or you can go on File, New and New Model. You can select any HIL device according to your benefit, or you can leave it as it is if you're not having the device at your end, because the model which we are going to make today, that is only using the signal processing components. So it is not going to occupy too much space and it will easily run on any of the HIL models. So I'm just leaving rest of the settings as it is. I'll click on next, and these are the settings which I've selected, and then I will click on finish. After this kind of a blank window will open in front of you. So now we will start making all the 5 subsystems which we discussed in the presentation. So first of all, what I'm going to do is I will input 5 subsystem blocks. If you search in the library, you will get this block of subsystem. If any of the participant is making alongside with me this model also, please let me know. If you're not able to match the speed, I will slow down the modeling. Otherwise, rest of you who are trying to understand how to do the modeling, you can just follow the way I'm doing it. So as you can see, I have dragged and dropped 5 subsystem blocks over here. So these 5 subsystems are basically indicated by these 5 subsystems. So the topmost is vehicle control, and rest of the 4 I've already mentioned. So I'm just going to change the name and keep it as it is mentioned over here. So this one I'm starting with, this is our lithium ion battery. So I'm just naming it as lithium ion battery. The next subsystem is basically, I think, drive unit, electric drive unit. Yeah. The third component which we are having, it is the mechanical transmission. Fourth subsystem, that is of vehicle dynamics. And the topmost was vehicle control and EMS. So all the 5 subsystem blocks we have already made over here. Now what we are going to do one by one, we are going to do the design inside each subsystem. So yesterday, as you had seen that Shamsher sir was doing the modeling, in which you have not used any subsystem block. Sorry. So in that you did not use any subsystem block. Your entire model was on this one screen only. But when we are using subsystem, it can be for multiple reasons. Right now, I'm using subsystem so that I have a good clarity about which part is indicating what component of the EV. So by naming it particularly a block, I am able to determine that what changes I have to do. It is also easier when you have to detect any error. So you will get a better idea that in which subsystem block you are getting the error, because every component you are designing separately. If you want, it's not a necessity to use this subsystem block, but later on when the entire modeling will be done, you will understand how clear and how neat it is to differentiate between every component which is going to be there. So first of all, I'm going to begin with the lithium ion battery subsystem. So I'm just going to double click on this subsystem, and I'm having these component inside the subsystem. So as you can see, if I double click on this, the name of this component is electrical port. So I'm not going to use any electrical component over here. I'm just going to use the signal processing library today. So I will just delete this component. And I want to use, first of all, one constant block. So I will take some constant source, just search for a constant. Then I'm going to name this as battery max voltage. So by name only you can understand that this constant block is representing what is the maximum voltage of my battery which I'm going to use today. So instead of using a particular battery block which is there in the library, I am actually designing the mathematical battery over here. Now I'm going to use one gain block. This gain is, again, I'm going to just rotate it so that I can do the designing. And I will just change the name and keep it as initial value. So basically gain is anything that this value is getting product with. So whatever value here I will provide, output of this will come as initial value. So I'm providing my initial value through this product block. It is getting product with the maximum voltage, and this will give me the battery output voltage. Again, I'm going to use two more gain blocks. And an integrator over here. So let me just connect these components. Okay, first of all, so now this initial value has to be provided to this integrator. First of all, let me just change the name. I'm going to put it as sign, because here I'm going to change the sign of the input which is coming to this block. And this is basically the capacity block. So this is, indicating the battery capacity to us. Now, there are many signals which are coming in and out of the subsystem. So we are going to use a lot of signal input and signal output blocks that you will easily find in the library. Basically, this is our signal processing library. All the components which we are using in today's model are inside this library only. So if we talk about signal input output, you can see you are having a lot of inputs and outputs over here also, type of input output, whichever you want to use. So let me just search signal input. It's inside the port block. So basically this is signal input. And similarly, we are having signal output. So let me just connect the output of this integrator to this signal output block. So right now you can see I have taken one input and one output. If I go back to the root means where I'm having all the 5 subsystems. So you can see right now it is indicating that there is one input in this subsystem and there is one output from this subsystem. So this is what the signal input output block is indicating, that what are the input output of this particular subsystem. Now there are few more input output which I will be using. So one by one I will be explaining which component is representing what and how they have been connected. Before that, I will just take one product block also over here. Now what I want to do is I will just connect the top part over here, and I'm going to change the sign to divide and multiply. So basically what I want, that this maximum voltage which is going, it should be divided, and what it should be divided with is this output voltage. So what is happening is I'm having this battery voltage. So basically using these components, I'm calculating some battery voltage. This battery voltage is the calculated battery voltage, and this is the maximum voltage. So what I'm doing is I'm dividing my battery maximum voltage with my battery voltage. So I'm going to get SOC. SOC, I hope you all are aware about SOC. Basically, battery SOC stands for state of charge. SOC is the indicator about how much our battery is charged. Basically, it is represented in percentage. Like in our mobile phones, we are having state of charge indicated by our battery symbol, where we can see our phone is 50% charge, 80% charge. So that is what is SOC. Similarly, for every battery, we are having this SOC component, and that is basically a ratio of the maximum voltage with the generated voltage. So that is what we are going to, mathematically calculate over here also. And that output we are going to provide to some other block. So now this is also one of the output. That is why I'm not going to use this block because this is for input. I'm just going to copy this output block and I'm connecting over here. So I'm just going to change the name. Instead of output 2, I am keeping it as battery SOC. Now this particular block also, as I already told, that this is indicating the battery voltage. So I've just named it as battery voltage. One more output I am going to take similarly of this block, that is also of the battery voltage only, but I'm taking it 2 times. Why? I will explain you in just a moment. Other than this, I am having this input block. So there is one input also which is coming inside this component. Now you can see I have 4 components in the subsystem till now. There is one input and there are 3 outputs. I have taken battery voltage 2 times, as you can see over here. The reason is it is the same value, but just for the ease of showing it in the subsystem, one battery voltage input is going to this electric drive and one will be going to this vehicle control. That is the reason why I have taken this value 2 times. I'm going to flip this block and I will be giving this input to the sign symbol. Now, if I talk about what is this input which is coming into the block, that is basically the battery current. So this battery current value is getting calculated from some other subsystem. Basically, by using all these 4 subsystems, we are calculating what is the current that is being given to the battery. And that current as an input, when it is coming to the battery, we are basically reversing the sign of that current. And that we are going to product with the capacity in order to generate what is the calculated battery voltage. So this is the kind of mathematics which is involved behind this design. Now I'm going to connect this initial value block also to my integrator, because it is going to integrate my battery initial value along with my battery capacity. And then we are going to calculate this battery voltage. So in order to take initial value, I'm going to select as external and click on OK. So as you can see, there is one other signal which is getting popped up over here. I'm just going to connect this initial value at X naught. By X naught also you can understand in mathematics we are studying that X0 or X naught value is representing the initial or very first component in any series. So similarly it is indicated over here also in this integrator block. Now, till now, I have only done the designing of the component and I have named each and every component. But now what I'm going to do is I'm going to feed the values in each and every component. So first of all, I'm having this battery maximum voltage. I'm going to put as 100.8. And I'm going to use the execution rate as TS. So this TS is basically an execution rate for this entire model. So instead of changing the execution rate value everywhere, I'm going to simply name it as a variable TS. And this TS I can simply define over here in the initialization script. This initialization script is valid for the entire model. So I don't have to change the execution rate again and again. Now, after this, I'm going to provide the initial value. So this gain block value is basically 0.90. Rest of the settings I'm not going to change. Then we are having this capacity block. Capacity is 1 upon 1.4118 E4. Basically, E4 is indicating, e to the power 4. In the sign block, I'm only going to change this 1 to -1 because whatever input is coming, that is basically a negative value and I want to convert it into a positive symbol. Now, I don't think I have to change any other settings over here. Rest of the settings are perfect. And our battery, this battery model pack has been designed. So this is our very first subsystem which we have made, and this subsystem is completed. So we have one input and three outputs over here. This one input, obviously, it will be coming either from this component or from this component. So one of the component will be giving one input to this battery block, and three outputs which are coming out of this subsystem are either going to this unit or this unit. So maybe you have got a better idea. Again and again, I'm explaining so there is no confusion. So now we are going to move to the next part of the subsystem, that is the electric drive unit. It is very simple. I hope you all are able to get an idea how to do the designing of every component of the subsystem. Just we are going to take few blocks and we are going to drag and drop them. And what is the mathematics involved behind it, that I'm going to explain step by step. Again, as this is a subsystem which is placed again between two subsystem blocks, so there will be some input which is coming inside this block and some outputs going out of this block. So first of all, what I'm going to do is I'm taking a signal input. So this is my signal input and I'm going to change the name and keep as battery voltage. So by the name only you have understood that this battery voltage is an input which is coming from the lithium ion battery pack. So this battery voltage I can directly connect over here, and whatever calculated voltage I will have, that will be fed to my drive unit or to my DC motor which I'm going to use in this model. Now I'm having one product block over here. Basically, in order to calculate torque, we are going to do some calculation. We need few outputs from this block. Basically, any DC motor is there, it is going to provide an output like torque output, speed output. Then there will be some back EMF measured. So that kind of outputs we are going to generate from this subsystem. Now we are having one sum block over here. So I'm going to take one sum block and I'm going to, instead of this 2, I'm going to write plus, minus, minus. So I have three inputs to this sum block. The very first input is connected to this plus, that is my battery voltage. And I will put a probe over here. I think I forgot to put one probe in the first subsystem. Yeah, just a minute. I will go back, and in my lithium ion battery, I'm having one probe also. So probe is like a, you know, it's kind of like a magnifying glass by the symbol, as you can see. And what it does is when we go to the SCADA panel, we can basically view the output through this probe. So whatever signal we are connecting the probe to, we can, actually see what kind of a signal it is and what are the output waveform. So this is basically the battery current measured, and we are going to view this battery current measure in our SCADA panel. Next, we are having this another probe over here, and basically this is the DC motor voltage measured. So As you can see, this is our battery voltage. Then there is some product which is coming over here. This product is basically generating the DC motor voltage. Now again, since this is a calculated voltage value, this I'm naming it as DC motor voltage measured, because we will have one reference and one measured value. Then only we are going to do the control. Whenever any control is defined, so we need to have a reference and a measured value, so that there is some error signal generated. That error will be given as a feedback, and then our system will work according to our control. Now I'm having one gain block again over here. So basically I'm connecting the output of this sum to the gain block. This is generating DC motor voltage. Now this sum block is having 2 to 3 components, and it is getting added. And what are the components associated with it? So first of all, I'm going to connect one more gain block over here, and I'm going to name it as resistance. This gain block, I'm going to change the name, and I'm going to keep as inductance. So right now what we are doing is we are just taking these gain. Basically gain means it is getting product, and then this value as it is we are going to use in our model. Instead of this gain, we can use a resistance block also, but the resistance block which is there, let me just show it. Resistor. So this is our resistor. I can put this also over here, but this is an electrical component and this is a signal processing component. So the color is also different. You can see this is indicated in black and this is the blue part. So we are not taking any of the electrical component in this particular model. That is why we are using the gain block for every value. All these values are fixed. We are not going to change the resistance again and again. Because if suppose there is an EV, if you have made a car, so you are going to buy one battery as well as one motor which is there inside your car. So that motor, it is having some internal resistance and some internal inductance value. So that is not going to change again and again, because once you have bought the motor, whatever characteristics it is having, that is fixed. So similarly, those fixed value we are just providing over here. So this inductance and resistance are basically indicating the inductance and resistance of our DC motor, which we are using in this particular example. Now again, I'm having one integrator block, because whatever we are calculating, we need to integrate everything together so that we can generate the torque signal. And then I'm going to take one more gain block over here. Now I'm going to connect it with my integrator block, and this is giving me one output signal. Now this output signal is going to go out from this block. So I'm going to use signal output port, and I'm going to connect it over here. So what is this output generated over here? This is the DCM torque, or the DC motor torque, which is generated. I am going to put a probe also over here, and I will just connect it so that we can view what is the waveform of this DC motor torque which is getting produced. So as you can see, it is showing some error that this component name is already specified. So just to show you all that we cannot have the name, we cannot have two names in the same manner in any of the model. So basically I have already named it as DCM torque. I cannot use the same name again for any of the component which is there in this model. So either I can just do the small change, like here instead of capital T, I'm using small t. So now it will be considered because this is a different name. But you need to keep in mind while modeling that you cannot have the same name. Even though both are indicating the same value, the same result will come in both, but you need to have different name. As you can see here also in battery voltage, it is the same signal which is coming out, but I have changed the name over here. One is battery voltage and one is battery voltage 1, because it will not consider the same name 2 times. Now moving on, I'm going to connect and rename this gain block also. So basically the name of this block is EM conversion. So this is electromagnetic conversion block. I'm going to provide a fixed ratio value over here, which is going to convert this electrical signal into a mechanical signal. So torque is mechanical. And what is the purpose of our motor? to convert the electrical energy into mechanical movement. So basically this EM conversion ratio is helping us to provide the exact calculated output which is getting generated in the form of mechanical torque. That is why we are using this EM conversion over here. Now, what I'm going to do is take few inputs also which are coming to this particular model. Signal input, because there are other components also involved for a motor. So this next component which I'm taking, I'm going to name it as DCM speed. So this is my DC motor speed, and I will take another gain block over here. Now speed is again a mechanical term or a mechanical component. So in order to if this sum block is having two inputs in the form of electrical component, so this component also we need to convert into electrical. That is why we are using this gain block. This is nothing but EM conversion block only. But what is the purpose now? But what is the purpose now? That this speed is getting converted into an electrical signal, and that we can directly connect with our sum block now. So I'm going to connect this block over here. Then I have this resistive block which is getting connected over here. And I'm having one output block, signal output. This signal output I'm going to connect over here. So what is this signal output which is being generated that we want to take out of this subsystem? Basically, this is the DC motor back EMF. So you must have heard about back EMF. Basically, any motor is producing this kind of an EMF. So this value also we are taking into consideration for this particular motor. So this is the back EMF which is getting generated over at this point, and that we are taking as an output signal, and we are going to give this to our controller or the control unit which we are having. Now, one last input signal that we are having, signal input. So the name of this signal is mod ratio. Mod ratio is basically our modulation ratio. So what is the need for modulation over here? Basically, we are having this kind of a motor, and we are going to do the conversion. We are having a DC motor, and we have a DC battery, and battery is always taking DC kind of input. So that is why we are not doing any conversion from AC to DC, or inverter we are not using over here right now. But this modulation is basically our you can understand like it is error signal or it is feedback signal, which is an input coming from the control unit to our DC motor, and the torque and speed is getting controlled by using this particular value. So mod ratio is basically determining the change in the torque speed, motor speed and motor torque, which is the controlled according to our drive cycle. So drive cycle graph, which I had shown over here, which I've shown over here. Using this graph only, it is being taken as a reference. According to this graph, a mod ratio is getting generated, and that mod ratio is then determining when the speed has to increase, when it is going to remain constant, when the speed is zero, and when it is going to deaccelerate. So you can see there are three cycles in this drive cycle. For some time, our vehicle is at zero or it is stationary, then it is accelerating, it is constant, and then it is deaccelerating. So this is what is the drive cycle, and this is what is getting followed over here in our model also. So all this change is getting as a feedback through this mod ratio to our DC motor. Now I'm going to use one product block over here. So one of the input of this product block is basically coming from this side. Okay, let me take a probe, because this mod ratio also, which we have taken, we are going to view this signal. So how we are going to view it, I will just explain. Okay, this is not, yeah. So This is the probe, and through this we are going to view this mod ratio also in our SCADA. Mod ratio reference. Now the output of this product block is going for a signal output, because something is getting generated out of this product block and it is going to go out of the subsystem into some other subsystem part. So as you remember, there was one input which was coming to this lithium ion battery, that is a battery current. So now using this mod ratio value, we are generating a battery current, and since the battery current is changing, the battery SOC will also change. So when the vehicle is moving, at that time, our state of charge will start decreasing. So the top part is connected to this mod ratio, because this is responsible for all the changes, and also this product block is also connected with this mod ratio. So this is how our battery voltage is also getting changed according to this mod ratio. Now this product, it is getting attached over here. So yeah, I think this part is also done. We are having one other component, that is a signal output component, which is basically connected over here after the product block, and this is indicating the DCM current or the DC motor current. This is not the battery current, but the DC motor current. So when this DCM current is product with the mod ratio, at that time we are generating the battery current. So I think I have named all the blocks. Yeah, most probably I've named everything. We will just check once again, once the values have been given for each block. So let me just start one by one by giving the values. So these components will not have any change in any of the properties. We will just start by inductance. So the inductance value I'm going to provide 1 upon 1 e to the power minus 3. So this inductance is basically 1 millihenry. Then I am having integrator block. So I'm not taking any initial value for this integrator. Then we are having the resistance block. So I'm providing a resistance of 0.08 ohms. This is my resistance for DC motor. Then we are using this EM conversion. So this conversion value is fixed, that is 0.2865. It will remain same for every component over here. So here also we are using EM conversion, again 0.2865. Okay, so all the components for this particular subsystem are also done. We have made this entire subsystem also. This is how we are going to represent a DC motor mathematically. So this is everything that is there inside the DC motor. Instead of using a direct DC motor, we have just done the mathematical modeling of it. So our second subsystem is also ready. I will just zoom it a little bit so that it's more clear for you all. Okay. Now I'm just going to stop for a few seconds and I'm going to check the chat if there are any queries. Okay, I have not received any queries. So participants, is anyone having any doubt or any query right now? You're free to ask.
No.
All right. So I hope you all are able to understand everything. If there is any doubt, you can just pause me and I will explain you again. Now we are going to move to the third subsystem, that is the mechanical transmission. So basically this is a very small subsystem, because in this we are only having the transmission ratios or the gear ratio, which is converting our transmission, basically the mechanical torque and the speed signal which we are having in accordance to the gear unit or the gear system. So now again we are going to use some signal input, because we are having some inputs coming from the previous block. So this input name is brake force. So by the name only you can understand that this is one input. Whenever this value is coming in input of this block, it is indicating that some force is applied so that the car is experiencing a brake and it will come to stationary position. So whenever we apply brake to our vehicle, it is getting stopped. So how we are going to like indicate it mathematically? There is one component called termination. So terminate means to end any signal. So the termination block over here is basically indicating that whenever a signal is indicating that there is a brake applied, at that time terminate everything means stop the vehicle. So this is one simple mathematical model. Now next we are having few more inputs. So the next input which we are taking is the DCM torque. Basically we generated some torque in the previous subsystem. We are going to take it as a reference input for this mechanical transmission. And there is one output block. So signal output. Basically, we are providing this output from this block, and this is getting as an input to the drive unit. The name of this block is DCM speed. So this speed block is getting generated from mechanical transmission, and it is going as an input to our DC motor. Now I'm going to use one gain block. I'm just going to flip it. And then it is coming from another signal input. Again, I'm flipping it and I have connected it with the gain block. The name is wheel velocity. Okay, so if my car or my vehicle is moving, at that time, the wheel velocity will keeps on changing, because obviously if we are applying brake or we are accelerating or deaccelerating, the wheels will move accordingly. So whenever this value of wheel is getting changed, similarly the speed of the motor will reduce or it will increase. So that is what we are indicating through this particular model. Basically this is an equation which is indicating that whenever wheel velocity will change, this wheel velocity is in some transmitted unit part, and that we are going to convert into a mechanical component, which is indirectly the DC motor speed. And according to this wheel velocity, our speed is getting changed. Now this gain block in between, it is representing the mechanical transmission ratio. So I'm just naming it like empty ratio 1, because I'm going to use one gain over here also, that is also mechanical transmission ratio. So now this speed is getting changed according to the wheel velocity, and when our speed is changing, the torque which is getting produced from the motor is also changing. So this is a feedback going to the motor, and that motor is changing the torque and giving an input over here. That is again getting converted using the gear ratio into a wheel force. So now I'm going to take a signal output block and I'm going to connect over here. Basically, this is the wheel force which is getting produced. Now, between these two blocks, I'm having one efficiency subsystem block. So I'm first going to use one subsystem. Inside this subsystem, I'm going to model my efficiency, but that I'll just do in a moment. I'm taking one signal input and one signal output. Now there is one signal switch over here. So if I search for signal switch, you will find it in the library by this name. Now this is basically, if I zoom into it, you can see it is having 2 points. Basically these 2 points are two conditions. Out of this, it will choose which condition is there according to the input, and this is our control command. So what kind of a control is there to choose either this input or this input? This is the purpose of signal switch. So just to make you understand why we are using it. So there will be two gain blocks connected to this particular component. I have two gain blocks. Then I'm having this signal switch. So first of all, I'm connecting this over here. Second, I'm connecting over here. and the output is getting over here. Sorry, this is not right. Yeah. Now, what are the name of these blocks? Basically, this is traction and this is braking. So as I told in one of my slide, what is traction force? The amount of force that is developed by power producing unit in the vehicle. So basically this is the traction force, or this is the applied force from the vehicle. So now we are having two inputs, either traction or braking. It means simply that when traction force is there, either the vehicle will move, maybe it will accelerate, maybe it will deaccelerate. But whenever braking force is applied, the vehicle is going to stop. So it will choose which of the condition is happening, and according to that, it will perform the operation of the switching. Now, what is a control command which is coming over here? So basically, I'm connecting this input signal to all my components. My control is also coming through this input signal only, and according to this only, my output is getting measured. Now, this signal switch output, I'm going to connect one termination over here. So what this means is this input is basically our DC motor torque. So whenever this torque input is coming, that is the control element. So if there is no torque at that particular situation, it will take the meaning that there is braking happening and it will terminate the signal. So basically the same output will go over here, that there is no torque. So the vehicle will not move. There will be no wheel force applied. In second case, when there is some DC motor torque applied over here, either it will increase or reduce. In the same manner, it is going to provide the input to this traction. And in that situation, we are going to take the input of this traction. And that only will be determining the output also. Whatever torque we are having over here, either it is greater or it is reducing or it is increasing. That output only we are generating over here. And then that torque is getting converted through this ratio, and we are having some wheel force. So this is the explanation about it. I'm just going to connect these blocks. Let me see if I have to change the name. Okay, I'm just naming this subsystem as efficiency. Now I'm going to provide the value of these gain blocks. So basically mechanical transmission ratio value is 15.0654. Rest of the value I'm not changing. Again, for this also it will same 15.0654. So these two values we have changed. Now if I talk about the signal switch over here, so basically this switch is having these three options. As you can see, it is saying pass input 1 if. So if my control command is this, the top part, this is the control command. So this is control signal. Then there will be some threshold value. So we are going to compare the control value with the threshold value, and we will compare it in 3-4 situations. Like you can see, either the control will be greater than or equal to threshold, or the control will be greater than threshold, or the control will not be equal to threshold. So all these three conditions are there. We will select what kind of a control signal we want to generate, and according to that, it is going to pass input 1. But if this condition is not true, it is going to pass input 2. So what is the threshold that we are going to use over here? That is 0.92. Just a minute, I think. Yeah, we are going to use 0 over here. And the condition which we are going to use is control is greater than or equal to threshold. So either the torque will be 0, in that case braking will happen, that is force will be applied and the vehicle will be stationary or it will stop. And if anyhow the control signal is greater than 0, then it is going to have some torque and the vehicle will be moving. Now the value of this traction and braking, so basically I'm going to use 0.92 over here, and for braking I'm going to use 1 upon 0.92. Rest of the settings I'm not going to change. Rest everything I will leave as it is. And now we have completed this subsystem also. So we have designed the lithium ion battery, we have completed the drive unit, and we have also completed the mechanical transmission unit. So you can see now we are having so many output and input signals which are getting generated. All these signals are going to play some role in our vehicle movement, and basically they are going to determine how much speed, how much torque our vehicle is going to have. And then when we will provide that reference drive cycle, then it is going to follow it. And similarly, we are going to observe many waveforms in the output SCADA panel. Now we have two more subsystems which are left. So I'm going to move to the next subsystem block, that is the vehicle dynamic block. Okay. So first of all, I'm having a signal input. This is my signal input port. I will change the name of the signal input to wheel force. So as you know that we were having this wheel force over here. So this wheel force is getting as an output and it is going to this vehicle dynamic subsystem. Then we are having a sum block over here. I'm connecting this wheel force with the sum block. Okay, let me just take 1 minute to have some water. Meanwhile, if you have any questions, you can drop in the chat box. Okay, so I don't think that anyone has dropped. Okay, there is one query. I can understand that in efficiency subsystem you took if else to accelerate and brake. Yeah, that's correct. But what about cruising? I'm sorry, I'm not aware about cruising. Can you explain what is this phenomena?
Yeah, so by cruising means when you accelerate and then you just leave the pedal of the throttle and then you just cruise at the speed. You do not apply brake. So if
You
you
mean to
want to,
say it is
yeah,
retaining the constant speed?
not retaining the constant speed. Yeah, means I understand in this drive cycle you will be using full acceleration or full brake. But
Yeah,
if we try to mimic the real life scenario, like
yeah,
when we accelerate and then we just lift the throttle of the pedal,
yeah.
then how can we simulate that here if we
In
want
this
to?
model, we have not done the modeling for that particular thing, but
Right,
if you will use the throttle value, then of course, mathematically, you can do the calculation and then you can like provide some particular blocks how you want to change it. You just need to provide some if else scenario only, right? So,
right.
like there is one condition in which your vehicle is accelerating, then one where it is cruising, one where is it deaccelerating. So for providing such kind of input, you just need to design some control logic. Now, for
Okay.
designing that logic, you can either use these logical operators which are there. So you must be aware with all the logical operators which are there. So
Yeah,
you
yeah.
can design your own controller according to whatever situation you want. Now, for
Okay.
cruising also, you want that there should be some limit. Like suppose I'm having this AND block, but along with that, I also want to use some greater than or lesser than, relational operator.
Right, right.
Yeah, so you will have many scenarios in this equal to, greater than, equal to, less than, equal to. So you can design the entire control, whatever you want. Here you can use two constant blocks maybe. Then you can define that between what speed to what speed is it cruising. So that kind of a scenario can be created. But for this particular model, we have not taken it into consideration.
Okay, okay, okay. Thank you.
Yeah. Okay. So any other question is there in the chat? Okay. So moving ahead, right now I'm going to take another gain block over here. That gain is indicating the mass of the vehicle. So of course, whenever there is a vehicle, we are having some mass associated with it, or the weight of the body of a vehicle. So I'm just going to name it as mass. Then again, I'm going to integrate that component. So we have one integrator over here. And we are going to generate some signal output. So what is this output now, which is getting generated? Basically, this is the vehicle velocity. Just a minute. Okay. I've taken the wrong signal output. Yeah. So the name is vehicle velocity. Now this vehicle velocity is again one component which is getting generated out of this vehicle dynamic subsystem, and we are going to provide this vehicle velocity as an input to our controller, that is the vehicle control unit. So this is vehicle velocity which we have calculated over here. I'm going to take this velocity 2 times because I have to provide it to two particular subsystems. One, it will be going to my control unit, that is this vehicle control and EMS, and one, it will be coming over here. Basically, in this wheel force, we will be providing that vehicle velocity also. In the wheel velocity, we are going to provide the vehicle velocity input. So I'm going to copy this block once again, and I'm taking this same output 2 times. Okay, now if I talk about, till now we have done the designing of almost 4 blocks. But as I talked about in the beginning, when I was showing you this slide, that we are having different kind of forces in our vehicle. So till now, you must have noticed that we have not taken these into consideration. Right now, what I'm going to do, till now we talked about tractive force, but we did not talk about resistive force. Now resistive force will also come into picture. So not in a very detailed manner, but yes, we have done the designing of the resistive forces in this particular vehicle dynamic block. So first of all, I'm going to take one product block. I'm just reversing it and I'm going to use 3. Okay. Now I'm also having one sum block. So in a moment only you will understand why I'm using all these. So even if like you can guess, there are so many different resistive forces which we have to add together so that we can create the net force. That is why I'm using the sum block. And behind each resistive force, there is one mathematical equation involved, and that equation is having so many product there are many product values which have to be used, and then we have to generate one particular resistive force. So that is why I'm using this product block. So okay, first of all, I'm going to take one constant over here. And over here, I am providing one gain. And I'm just simply connecting it with this sum block, number 3rd. So what is this? This particular blocks are representing the grade force. What was the grade resistance? Whenever vehicle is going up or down a slope. So what is this constant indicating? That what is my road slope in terms of percentage. But right now for this model, we are not taking any road slope. Why? Because we have already defined a drive cycle for this. So we are considering that it is moving in a flat surface. So that is why we are not taking this into picture. But yes, if you will change this value, it is also going to play some role in this particular model. I'm going to keep it as 0 and I'm changing this to TS. After this, I'm having this block. Basically, this is a mass and gravity block. So if suppose you design the model and you want to have some slope also in your road or in your surface, so that road slope then product with mg. So basically mg, and then it will be the percentage of whatever slope you're providing, or that is the angle. Here we are providing it in the terms of percentage. So that we are going to provide, and we will product it with mass and gravity and provide it in the sum block. So this will, in order, in total, it will generate the grade resistance. Second, what we are having is rolling resistance. So the rolling resistance is basically fixed resistance, because we already know what kind of wheel we are using and what is the road surface we are taking. So we have provided the fixed constant value for this force. Third, what we are considering over here is, again, I'm taking a constant, and that is the aerodynamic resistance, what I'm going to use. So I will just name it so that there is no confusion. Rolling resistive force. And then this is aerodynamism coefficient. So instead of using a constant aerodynamic force, we are actually calculating the aerodynamic force, because when the vehicle will be moving, there will be some interaction with the wind, and the air will be passing through, and we are taking that into consideration. But how to do it, like how to model it mathematically, that we have taken into consideration. But for this case, we have taken the wind speed as 0 only. So I'm just going to define by using a constant, and I'm taking termination over here. So again, this is 0. This is TS. This is wind speed MPS. So you can understand that wind speed is 0, and that is getting terminated. So if we are using this value anywhere, so it will be considered as 0 only. Now, you must be wondering that we are taking road slope also 0, wind speed is also 0. So then what is the purpose? So basically, this is an automated example which we have designed in order to show you that how a system is working when there is some sort of reference provided, because here our drive cycle is our reference, so we are not changing anything. But all these changes can also be provided in the reference. So you need to design a very good controller for your vehicle, whatever kind of vehicle you are designing. You need to have all, if you want to take everything into consideration, you need to design a very good controller. Here we are not using a very complicated control logic, and that is why we have taken many values as 0, because we are using a very simple reference over here. Okay, so now this vehicle velocity is also connected in this subsystem. And we are having this aerodynamism coefficient. So this vehicle velocity along with this aerodynamism coefficient is producing our what is that, aerodynamic force, I think. Yeah, aerodynamic force. So you can see in this equation we are having v square, then we are also using the value of air density rho. So this rho value is basically the aerodynamism coefficient which we are providing. Wind speed is 0, and velocity we are taking 2 times because it is v to the power 2. So that is why we have taken v square. And then we are going to calculate some aerodynamic force over here. So aerodynamic force plus the rolling resistive force plus the grade resistance force, all three are combined to determine what is the net force. And we are also taking one signal over here, which is the acceleration force. Basically, okay, let me just represent it by showing. We are taking one signal switch. In this signal switch, we are having 2 inputs. The first one is connected over here. Then we are having one constant also. This is again 0. This is the resistive static force. So basically this signal switch is determining what is the net force which is generated, and that net force we are going to compare with our tractive force. We are having this resistive force, and then we are going to compare it with the tractive force so that we can determine what is the net force. Here we are having one absolute component. It is indicated by ABS. Okay. Yeah. So you can see this is the control logic which is going into this signal switch. And this control is basically also coming from vehicle velocity, where we have taken this mass also into consideration. So acceleration is basically provided through the speed reference, which is there in our drive cycle. But mass we have taken over here in consideration. And mass will anyways be taken into consideration for all the forces, because weight is going to play a role in every force. That is why we have used this mass block over here, and we have given it as an input so that it is product with all the forces except this force, because road slope is 0. So we have taken mass and gravity together over here also, but it is not going to create a difference in the overall output. Now I'm going to take one signal output port. I've connected it with the output. And we are also going to use one probe, because again, what we want to do is we want to see this signal generated in the SCADA when we are going to make the SCADA panel. Okay, so I think we have done the entire modeling of vehicle dynamics also, but we just have to provide the values. So I have not given the values for any component till now. I'm just putting it more clearly so that we can have the entire model and we can see what are the signals very clearly. Each and every block is generating so many different signals. And this will be the main component, because this is the entire controller. How we are providing the drive cycle and how our drive cycle is changing everything, like all the signals which are associated, that we are going to see when we will make the vehicle control. Okay, so one by one we are going to change the values. First of all, let me see. We are having this mass. In this, I am using 1 upon, in the bracket, I'm using 692. Basically, the vehicle mass is 692 kgs. So we are using it 1 by, anyways, we are like determining what kind of a mass we are going to use for our vehicle, but that is not going to play a role in this example, because we are having a reference pre-decided for us. So our mass is also not playing a role in that, but everything can be taken into consideration. That is why everything has been designed in such a way. You can use this as a reference for designing your vehicle, and you can change all these values and you can provide whatever input according to your application area you want. Now what I'm going to do is, in the absolute part, I will leave the execution rate as inherit. Okay. In the switch, I'm going to provide the condition as control greater than threshold, and this will be threshold will be 0.5. Okay. Resistive static force. Okay, this is 0. This is inherit only. Okay. Then integrator block is there. For terminator also we are going to use TS. Wind speed constant we have already given as 0. Okay, I will leave this to inherit. Then we are having aerodynamism coefficient. So aerodynamism coefficient value is 0.428. And this I have taken as TS. Next, I'm having rolling resistive force. So now this is the rolling resistive force. The value is 135.77. So this is total calculated rolling resistive force. We have not taken each component separately. The execution rate for the model is TS. Road slope constant is 0 and execution rate is TS. Mass and gravity, it is 692 into 9.81. 692 is the mass, 9.81 will be the gravity, and I'm going to divide it by 100 because our road slope is in percentage. So I think we have given all the values over here. Let me check once again. Okay, this sum block is not connected right now. So we are connecting this sum block with this component only, that is the vehicle resistive force. Okay, maybe I have not changed the name at this part. First of all, this is wheel force. We also have a probe over here. The name of the probe is vehicle tractive force. So vehicle tractive force. Then we have this output. Basically, this is vehicle resistive force. And since we are viewing the resistive force also, vehicle resistive force estimated. So this is the part which we have left. I think we have named rest of the signals correctly. Yeah, so now this is fine. Now we are only left with one last component, that is a vehicle control unit. Also, one thing more which we are going to do is we will be providing the image to each subcomponent. For example, I have used 5 images over here. So what I have done, each and every image I have saved in my system. And let me show you, I have created one folder over here. In this particular folder, sorry. Maybe I have skipped it. Okay, this is the EVSP. Yeah. So I have created this folder. In this, you can see all these images I have saved in this folder only. Now, what I'm going to do before designing further, I'm going to save this model. But while saving, I have to keep in mind that I'm saving my model in the same folder where I've saved all these images. Because what I want is I want to use these images in my model. So it is going to extract the image from somewhere, any location in our PC. It is much easier if you save those images in the same folder where you have saved your model. So it will be easily able to fetch. Otherwise, sometime it may show some error also. So I'm just going to save my model. Save as electric vehicle. The desktop EVSP, I'm going to save the model. So if any of the participants are making the model alongside, please remember to save the model. Is there any? Okay. So far, we don't have any further questions. So now we are going to start with the last component, that is a vehicle control and EMS. This is also a big component and many parts are there inside this. And we are also having the drive cycle input associated with it. So probably we will do the designing of one part of this, and further we can continue tomorrow also, because it will not get completed in today's time. And once we have done the component design for this vehicle control and EMS, we will provide the image for each and every component block. Then we are going to compile our model and we will check whether there are any errors. Once all the errors are rectified and there are no problems in compiling the model, we are then going to do the entire SCADA panel modeling. So SCADA for this particular model is not very complicated and it won't consume much time also. So that particular modeling we can do tomorrow. So let's start by doing the vehicle control and EMS part. So first of all, this subsystem component I'm going to delete because that is the electrical part. Now I'm going to first of all take one input over here, that is the signal input. The name of this input is battery SOC. So if you remember, first block which we made, that was the lithium ion battery block, we were calculating the SOC at that time. And that SOC is coming inside this control logic. So basically the battery SOC, we are going to check what is a battery SOC. So that is getting calculated and that is coming inside this control logic. Now we are having one signal switch. And we have one gain block. So earlier when we calculated the SOC, it was not in percentage. It was just an normal numerical number over here, if you will see. So we have not used multiplied by 100, or we have not termed anything in the terms of 100. So whatever battery SOC will be calculated, it will not be in terms of percentage. In order to convert the battery SOC in terms of percentage, we are using this gain block, and we are just simply naming it as 2% to indicate our battery SOC in terms of percentage. Now we are using one probe block. So I've connected this. The name of probe is battery SOC estimated. Okay. Now for this signal switch, basically this is SOC is the input control for this signal switch, which is going to act as a switch for electric braking. So two inputs are there. Both inputs will be provided by constant block. The value will be 0 only. Let me just hide the name. Okay. Kept it like this. So this is electric braking. I'm using 0 and TS. Again, this will be 0 and TS. And I'm just connecting it with the signal switch. Over here, I'm having one signal output port. So this is a brake force. Now, if I want to understand the condition for this signal switch, let me just check. Okay, so I'm going to use the condition control is greater than or equal to threshold, and the value used will be 0.9. So whenever this battery SOC value, it is getting greater than or equal to 0.9, the control logic above the threshold value, then it is going to show the value of that particular SOC, and that control signal is going to pass input 1, else it is going to pass input 2. So this logic has been defined only when we are going to have the electric braking, or we are going to apply the brake force. So this output also which we are generating, basically this is the brake force only. And this brake force, if you remember, we were having this situation over here where one input of brake force was coming and the vehicle was getting stopped. So we have determined that our SOC value should be in the range in such a way that our control should be greater than or equal to 0.9 or the threshold value. Whenever this situation is there, at that time, it is going to show this pass input 1, otherwise it is going to pass input 2. Either way, this is going to provide one input signal for brake force, and whenever this brake force will get some value, at that time the termination will occur and the vehicle will stop. So this is one of the logic which we have basically designed in order to do the modeling for brake force. Now this is a separate part in the control unit, and now if we talk about drive cycle, that will be a different part. So before going into the detail of the drive cycle, basically I hope you must be aware about how a controller is getting designed. I think I just discussed earlier also. So just I'm going to use one comment over here. Add comment. Okay. So whenever we are using some control logic, so it is having some reference value minus the measured value. So this is most basic logic for determining the control, and we are using many types of controllers, if you all must have studied. So as you can see, if we talk about control, in signal processing, we are having this PID controller. This entire model has been made using signal processing component. So if I talk about this PID controller, sorry. So if we talk about this PID controller, this is one component which is already pre-existing in signal processing library. So let me just discuss what are the features inside this component. We are having this type of controller. So we can select what kind type of controller we want to use, either PID, PI, PD, P or I. So in this PID, you must be aware P stands for proportional, I is for integrator, and D is for differential. So we are going to use this type of a control logic. In this, we often provide the value of Kp as well as Ki. The value as well as the source can be externally provided also, or you can provide it through the SCADA also. You can do the tuning of Kp and Ki value as well as Kd value also. Now, if we talk about filter coefficient, so we are having this fixed coefficient value. We can also provide the integrator initial condition and the filter initial condition. Then we can generate what kind of signal output we want, whether it is a real integer or undefined integer, whatever value, and execution rate. If we talk about advanced, so there is the option of limit. So you can either set the limit true or you can have it at false. So if you will set it on true, you can define what will be the upper saturation limit of your controller and what will be the limit lower saturation limit. You can also use this one feature which we have of anti-wind up, basically for getting a more enhanced signal in the output. And this also again you can use internal as well as external. So you can provide it externally also. Then we are having this reset option also. You can select what kind of a external synchronous reset you want to provide, rising edge or falling, either or level, any kind of reset also you can provide. Why I am explaining this block? Because we already have this PID controller block, and if we want, we can use this PID controller for our control logic. But because everything we have modeled in this particular model today, which we have made, we have done everything mathematically. So this PID logic also, we will be doing it mathematically. What I mean by mathematically modeling it is that instead of using this block, we will be going to create by using some gain block, by using some constant block. We will be providing this Kp value separately, Ki value separately, one integrator we will use separately, then we will give some initial condition to that integrator, then we will use one limit block separately. Everything we have over here in our library. As you can see, we are having the limit block is there. So these are also a part of signal processing library only. So there are two ways of like making the entire controller. Either you can use this pre-packed component which we have in our library, that is PID controller, or you can use these separate components also. So just to give you a brief about how the control logic has been made. Now, before doing the entire control, basically, of course, we are going to use the control logic, but we are having the drive cycle input. How we are providing the drive cycle input? For that, I am also going to show you that this is the folder where I have saved my entire model. So right now, when I've saved, I'm not sure why it is not showing. Okay, let me just open this folder again, because just now I've saved the model, it should show. Yeah, so now it is showing. So whenever we are saving any Typhoon schematic model file, it will show in this way, .tsc. So .tsc file is basically the schematic editor representation. In this, you can see we have images, as well as you can see there is this word file. This word file is basically indicating the drive cycle inputs and outputs. If I just open this file, I want to show you. These are some of the input and output X and Y values which we are going to use. Using these values only, we have created this graph. Like if you want to see, then we are having the inputs and outputs of this particular graph, which have been used by these values only, and we have created that curve. So this is what is the X and Y value which we are going to input in our model. And this will act as a reference when we are drawing the controller. So first of all, I'm going to take one clock over here. Why we have taken clock? Because according to these input and output reference values, we have to determine that what is the simulation time of our model, because by only providing xy values, we are not going to compare it with our model running time, but we want that this drive cycle should run in the entire simulation time that we have provided for the model. So that is why I'm using this clock symbol, and after this clock symbol, I'm going to use 1D lookup table. So you can see this is one block which we have. I'm connecting the clock with this 1D lookup table. I'm just going to change the name and I'm going to keep it as ECE driving cycle. So now you can see this is my drive cycle input. So basically, what is 1D lookup table? If you want to know in detail, you just have to click on help. You can go inside the detail about this component. So if you see, we are having the description that we are having some X values and we have some FX or Y value. And according to that, this lookup table will generate the output, which will be either in the form of this graph also, for which we can provide multiple points of X and Y. That is the only use. And other than that, we have few more options in this lookup table. Like you can see, we are having the type of implementation method. So implementation can either be equidistant or non-equidistant according to the X and Y value which you are providing. Then we have extrapolation method also. You must be aware about extrapolation. And in this, we have the option of clip as well as linear. Then we also can define what is the execution rate over here. So here in place of input value X and in place of output values Fx, we will be providing this X and this Y value. So these are some sample values which have been taken for our drive cycle. Just a minute. Yeah. So right now I am not going to input those values. I have just taken the component right now. First of all, what I'm going to do is I will take one gain block over here. I'm connecting it with my drive cycle and I will connect a probe over here. So this is connected. Now, what is this representing? Okay, so we have defined what is the time for which our simulation is running. We have also given the reference of the speed. Now, this is going to generate the speed according to our model time. So basically, it is the reference speed which is generated, but how do we determine the unit? So what we are going to do is we are going to convert it to kmph. Sorry. So I'm going to convert the speed to kilometer per hour, and that only we are going to see in the probe also. So I'm going to name it as requested speed. Why we have named it as requested speed? Because this is the speed which we are requesting according to the drive cycle, and what we are getting from the model, that is a measured speed. So basically this requested speed is going to act as the reference value, and whatever measured we are having in our model, that is going to come as another input, and that will be our measured speed. Then we are going to compare both the speed, and for comparing, as I already told, we are going to determine one kind of a PI logic. Okay, so there will be one signal input port. I will just name it as vehicle velocity. So this velocity now, this is basically the vehicle velocity or the vehicle speed which is coming from the measured quantity. So we are measuring this and we are going to directly give it as input. Over here also, I'm going to take one gain block and one probe. Again, I'm changing the name to kmph, and this probe will be vehicle speed. So up to now we have taken two inputs. Now we want to compare these two. because this is reference, this is measured. So here I'm going to take one subsystem. Subsystem I have taken. Inside this subsystem, we will have two values and one output. So what I'm going to do, I will enter the subsystem. I'm going to delete this. Then I'm going to go into the ports, signal input port. So two inputs will be there. First, the name will be reference. Second, the name will be measured. And there will be one output which will be generated from this control logic. So right now I am not doing anything inside this controller. I'm just going to come out back to my main controller logic window. This I'm going to connect over here. So my subsystem first part of the reference speed has been connected, and the second part is going to be connected over here. So my reference and measured will go inside this PI controller, and I will get one output. I'm going to name the subsystem as PI control. Then I'm having one sum block over here. So I will use one sum. I also have one input again coming from here. So I'm using one signal input port. Now what is this signal input port indicating? This is indicating vehicle resistive force. So if you remember, we were doing the entire modeling of the resistive forces in vehicle dynamic, and we calculated this vehicle resistive force. This is coming as an output over here. Now, what is happening is we are going to provide this vehicle resistive force to the sum block. This is also the resistive force which is calculated according to the control logic after determining the drive cycle. So again, we are using this sum block. We are adding the resistive force, and then we are using a gain block over here. This gain is now representing the empty ratio. The value is same what we used earlier. So basically this is mechanical transmission ratio. So now we are going to convert this particular component into mechanical component. So right now it was in the terms of force, and this force is getting converted into the mechanical unit, or we are going to basically generate the requested torque out of this gain component. So I'm going to connect one probe over here, and I will just connect the empty ratio with this probe. I'm going to name it as DCM torque requested. So why I'm using this term as requested, like requested speed and requested torque, because according to drive cycle, this is what is desired, and measured will be obviously different from this. Now this is, again, this is torque. So this is a mechanical signal. Now we again need to do one more conversion, that is from mechanical to electrical, in order to interact with the electrical components now. So for that, we are going to use few more gain blocks over here. So first I've taken one gain block. The output I'm going to connect with probe. So I've connected the output. Then I'm taking the name I'm going to change. So this is EM conversion. As I've already told, it is converting the mechanical torque into an electrical signal. Now, what is the electrical signal which is basically converted over here? This is the DCM requested current. So what is the amount of current that will be provided to our DC motor? So this component is going as an input to this particular block, because this is our drive unit. We are having the DC motor inside this. So you can see we are having this DCM current component. So that will be used, and we will be generating that value also from here. So we are going to view that signal in the probe. Again, this EM conversion block, I'm going to just copy. Then I will be taking another input signal. Okay, just let me place it like this. I have signal input. The name of this signal input is DCM current. So if you remember, we calculated the DCM current in the motor. This is the output of DCM current. This we will be feeding over here in the controller unit. So this is the measured value of the current, and this is the calculated value, that is the requested value. So again, we have to compare both the values. So what we are going to do? Again, we have to design a control logic over here. Right now, I have not designed any PI control logic. I will be doing it once I have done the model part. Just let me drag these components so that everything comes in the same window. Okay, this is not going to work. So what I'm going to do, again, I will be taking one subsystem over here, because again, I'm going to do the same thing. The measured as well as reference will be compared using a PI control, and it will be generating the output. Again, I'm deleting this part. I will take 2 inputs and 1 output port. Sorry. This one will be reference and this one will be measured. Okay. So my reference will be provided from this signal and my measured will be from this. I want to view this signal also. So I'm connecting a probe over here. This probe will be connected to my signal. And I'm going to change. Okay. Yeah. I will be naming it as DCM current measured. Then I'm also having one sum block over here, similarly like we made over here. So I'm having one sum block. Then 2 more further inputs which we will be considering, that are also coming from other components of the subsystems. So we were having, 1 minute. Two more components. So signal input we will be using. This one is the back EMF. If you remember, we were taking the back EMF also into consideration. So DCM back EMF, and then another input which we were having, signal input. The name was battery voltage. So if you remember, I told in the beginning we have taken battery voltage 2 times because we are giving one part of that battery voltage in this particular block, and one we have provided in the drive cycle. Sorry, the motor drive unit. Yeah. So this is a bit more complicated subsystem, because this is the biggest subsystem, because it is controlling everything and everything is associated with it. The inputs are coming inside this subsystem from almost all the subsystems, and then it is providing some output also. That is why it takes a bit of time. and I think only 10 minutes are left. It is better if we will continue tomorrow creating this subsystem further, so that there is no confusion, because all the major things we will be doing tomorrow. At the end, we are going, what I'll just tell you in short, that at the end, what we are going to do is we will be calculating the mod ratio. If you remember, we were having this mod ratio over here. This was one input. So basically, this is coming from the control logic, and this mod ratio was then in turn changing everything. This mod ratio was responsible for the input when we were calculating it with the battery voltage. That is in turn changing the torque and speed. So in a way, just to explain you, whatever output of mod ratio is getting calculated in this block that we will design tomorrow, it will be consisting of the drive cycle which we are providing as reference, as well as the measured values. So you can see how everything has been connected and associated together, because that mod ratio will not only consider the reference value but also the measured values. And then we are going to do the modulation, and our speed is going to change in this manner that for some time the vehicle will be stopped, accelerating, deaccelerating, repeating it, and every time the speed will be increasing also. So it is going to follow the same steps for 3 times, and then probably we will find the right output. So our vehicle should follow this particular graph only. That is our aim. Tomorrow, what we will do is we will define the PI controls for both. We are going to do the connection and complete the mod ratio part. Then we are going to interconnect all the subsystems. We will place the image in each subsystem, and then we will compile the model, and then we are going to go with the SCADA. So the SCADA, as I already told, it's not very complicated. So easily we will be able to complete the model tomorrow. And if we have some time remaining tomorrow, so there is one more electric vehicle model which we are having, which is not made using signal processing component, but by actual components. Like there is actual induction motor, actual inverter, which has been already designed by our development team. So if we have time remaining left, I will show that model also to you. I can demonstrate that, so that you can get an idea that when you are designing that by using physical components, like you are having a physical inverter and you're having a physical motor, all those physical real life values you can provide in the model, and you can see how it is working. And as you were talking about the throttle value also, somebody has asked. So that also we are changing in that particular example. Why we have not considered it that one for this workshop? Because in that we are not providing any reference. So that is not actually coming in the part of unmanned vehicle, because there we are giving the manual input for speed and throttle value. Then we are having some uh, regenerative force which is getting generated, and then batteries charging through it. And we are also having the grid supply and charging station in that. That is why we have not considered for this workshop. But yeah, we can have a demonstration of that if you all are interested. So let's see if time will permit us. So for now, I'm going to stop the session over here only. If anybody has any queries, you can ask me in the chat. Otherwise, I think we can conclude for today.
Thank you for the session, ma'am. Uh, Ma'am is now ready, will now be ready to answer your queries, if any pertaining to today's topic.
Okay, I don't think there are any queries. Just one more thing, if anyone is making the model alongside, please remember to save your model also, so that you are not losing the entire data.
All right, then. I would like to thank you for taking the time to deliver this informative presentation, Mr. Bajpai. And I would like to thank all the participants for joining us this afternoon. Thank you for joining, everyone. Have a great evening. Bye-bye.
Thank you so much.